So I'll talk today about since it's a conference about symmetries, I wanted to talk about some very nice examples where just general ideas from symmetries and topology are useful to constrain the dynamics of defects. So the structure of this talk is that at the beginning, I'll introduce some terminology and the basics of conformal defects. And then I'll prove several constraints on the infrared limit of conformal defects. And then I'll show you that these theorems can be applicable for magnets, just defects in ordinary magnets, and where I'll try to establish two results about defects in magnets using these general considerations. So let's begin. These papers are not all directly relevant. So they're just in this, these are papers that I participated in with ideas that are related to this talk. But perhaps the most closely related paper is the one that is going to appear very soon here, with Ofer Aharoni, Gabriel Cuomo, Mark Nezay, and Via Raviv Moshe. But I'll also quote some results from this paper, this one, and this one. Okay, and also if there are any questions, I assume that there is a way to take questions. If there are any questions, please just interrupt. Okay, so the introduction is the following. Conformal field theories arise in the condensed matter world from quantum critical points. So you take some system at zero temperature with a Hamiltonian, you tune the parameters, and all of a sudden, for some special choice of parameters, you get a diverging correlation length. And in many cases, the dynamical exponent is 1. So you actually get a relativistic conformal field theory at long distances at these special points. So that's one way in which conformal field theories arise in physics. They arise as these zero temperature quantum phase transitions. Now, as far as the systematic study of conformal field theory goes, there has been probably 5 decades or so of work on how conformal field theories constrain the correlation functions of local operators. So local operators come in some representations of the conformal group, and people have worked very hard for many decades to understand what this implies. There is a whole theory of critical exponents. There is a whole theory of the bootstrap equations. So you can say that a lot is known about the space of local operators. There is a lot of data for many examples. However, the questions that concern with defects in conformal field theory are far less explored. And the simplest case is a line operator. So it's not a local operator. It's not codimension D. It's a codimension D minus 1. It's a line operator. And so it's you can consider it as an infinite line, or you can think about closed lines. We will discuss both later on. So these defects, there is some space of defects and very little is known about it in general. So historically, the subject of defects has been very important in the historical development of the field, because Wilson came up with the ideas of the renormalization group, thinking about a very particular defect that is called the Kondo defect in 1+1 dimensions. And also defects were one of the first examples were integrability. So integrability in quantum mechanics is known for since Bethe probably, but the fact that it carries to continuum quantum field theory was demonstrated perhaps. One of the first examples was in the context of defects. The ideas of the conformal symmetry historically came from the Kondo problem. But all of this was more or less in 1+1. And very little is known about even line defects in higher dimensions. And that's the subject of this talk. Let me also mention that in the condensed matter interpretation, if you orient the defect in the time direction, then it's localized in space. And they call it, condensed matter people call it an impurity. So because it's just a point like defect in the, so it changes the Hamiltonian in a way that is localized to one point in space. You can think about it as just a modification of the theory by some new term in the Hamiltonian, like in this example. So if you just slice in the space-like direction, a line defect looks like a perturbation to the Hamiltonian, and this is some kind of paradigmatic example where you put some garbage at one point on the lattice and you couple it in some way to the rest of the lattice sides. So that's how defects arise in condensed matter, as just impurities, point-like impurities. So let me just say one more thing before I ask if there are questions. So what could be the infrared limit of a line operator in conformal field theory? So one option is that we get a non-trivial conformal impurity. I will define what it means in the next slides. That basically means that there is some kind of response to this line defect, which affects the bulk in a way that decays as you go further away from the impurity. And the correlation functions in the presence of this impurity obey some conformal group, which is smaller than the full conformal group. Another option that is much more familiar from the study of symmetries is that the line defects become topological. So it becomes a line operator that's topological, so it generates some sort of higher symmetry. That is a possible possible scenario for what the infrared limit of a line operator could be. It could be some topological operator. Like in Chern-Simons theory, we have tons of topological line operators. Another option is that it could be completely transparent. So that means that the line operator cannot be detected by any bulk observable, neither by local operators in the bulk, nor by extended operators in the bulk. So in this case, the line operator is almost the unit operator, but one has to be very careful, and it will be important for this talk, because even if it's completely transparent, it could still be slightly non-trivial. It may not be exactly the unit operator, because you could stack it with a 0 plus 1 dimensional TQFT. A 0 plus 1 dimensional TQFT is essentially just a discrete set of vacua, which are degenerate. And it's like a quantum mechanics on the line. You put quantum mechanics at this impurity, and this quantum mechanics happens to have a few degenerate ground states. So even a completely transparent line could carry vacuum degeneracy, which you can interpret as a 0 plus 1 dimensional TQFT stacked on the impurity, stacked on the unit operator, I mean. Okay, are there any questions about the terminology and the general introduction? Okay, I assume there aren't any. So what is a conformal impurity? So a conformal, a line operator is said to be conformal if it preserves a subgroup of the conformal symmetry. So in particular, the important piece is this SL2R, which acts on the line operator like Mobius transformations. The SOD minus 1 is transverse rotations to the line, and it's not strictly a necessary condition for a line to be conformal. There are examples of conformal line operators that do not preserve the transverse rotations. But by definition, they have to preserve an SL2R symmetry. So a line operator doesn't have to be conformal. We expect that many line operators become conformal at long distances. So even if the bulk theory is tuned to a quantum critical point and it's conformal, a line operator doesn't have to be conformal. It could preserve a much smaller subgroup, which essentially just means energy conservation. This is time translation invariance and transverse rotations. So at long distances, you could recover SL2R. So the line may become conformal, or it may become topological, or it may be completely transparent. And the central question about defects in conformal filter is to understand which ones are transparent. Sometimes instead of the word transparent, we say screened. Which ones are topological, which ones are conformal, and how many conformal line operators are there in the first place. Okay, so the SL2R symmetry is essentially used to classify operators. Bulk operators away from the impurity are classified by the usual conformal group, but operators that sit at the impurity are classified by SL2R. So operators on the impurity have their own scaling dimensions, and they have their own operator product expansion coefficients, and they have their own transverse spin if there's a if this is a symmetry. So in this picture, if this red blob flows, yes. Is there a question? So if this red blob flows to a conformal impurity, then operators on this red would be classified by SL2. This is the terminology. One very important concept is that we can expand bulk operators away from the impurity as a power series in terms of defect operators. So defect operators will carry a hat. I hope I'm consistent with this notation, but I'm afraid I would not be. Anyway, I hope there will be no confusion. So defect operators only depend on time, while bulk operators depend on their transverse location and time. And you can do a you can do a Taylor expansion, or well, it could be also a singular. There could be some singular terms here. They depend on the scaling dimension of defect operators and bulk operators. And this is consistent with SL2R. Now, if you look at experiments for quantum critical points with impurities, one of the most interesting observables is just the one-point function. In ordinary conformal field theory, of course, one-point functions are zero because there is no way to put something that has scale. But in the presence of an impurity, there is an observable coefficient little a, and the one-point function decays as you go further away from the impurity as a power law. So this is a very important observable a that is completely physical, and this is one of the main things that are being measured when people have impurities in a quantum critical point. So this term comes from the unit operator in this expansion. So one of the defect operators is the unit operator. And if the coefficient of the unit operator is non-zero, then we have a one-point function. A very important defect operator that always exists when the defect is non-trivial is the displacement operator. And here I forgot to put a hat. It's a defect operator, so it depends only on time. And it has a protected scaling dimension, which is exactly 2. And it has a very simple physical meaning. Remember that we discussed so far the setup where the defect is a straight line. That means that it's an impurity that's localized in space and never moves. But if you wanted to change the space-time curve, so it could describe a moving impurity, and you could be measuring the response to a moving impurity. So this is what this displacement operator is good for. The displacement operator is used to change the space-time shape of the defect. So inserting the displacement operator on the defect is equivalent to changing the space-time curve. So one piece of terminology that is equivalent to what I already said is that if a line operator has a non-vanishing displacement operator, then it's a conformal line operator, most likely in the infrared. Well, let me just rephrase it. If the displacement operator is non-vanishing in the infrared, then we say it's a non-trivial conformal line operator. But topological line operators obviously have no displacement operator, like line operators in Chern-Simons theory don't have a displacement operator. And obviously also completely transparent lines don't have a displacement operator, it just vanishes because the system doesn't care where you put it, if it's topological or if it's completely transparent. So the displacement operator is a very nice gadget that allows you to decide if a line operator is trivial or non-trivial. You just have to ask if there is a non-trivial response to displacing the impurity. Okay, this finishes a little bit more of the introduction. Are there questions?
Is there any constraints on delta hat? Are the same ones?
Delta hat is the scaling dimension of the defect operator under SL2R. And for the displacement operator, it has to be exactly 2.
No, I mean in general for any defect operator. I mean,
well, it's a part of the data of the conformal line operator. And you could say that not much is known about it. Of course, we have examples which we have, epsilon expansion, 1/n expansion. So there is some data, but it's a set of numbers about which we don't know anything a priori. It's constrained by bootstrap, but the constraints are very weak. Well, unitarity constrains it to be bigger than 0. That's one thing you can say. Okay, now I'll show you how using symmetries we can constrain the dynamics of defects. And then we'll go to examples in magnets. Suppose we have a system with a one-form symmetry. A conformal field theory with a one-form symmetry. So an obvious statement that's almost by definition, is that a charged line operator, I mean under the one-form symmetry, cannot be a transparent line operator. It's a tautological, because the way I define transparent line operators is that they're completely transparent to all bulk observables. Yes, they're completely transparent to all bulk observables, local and non-local bulk observables. So of course, if a line operator is charged under one-form symmetry, it cannot be completely transparent. Condensed matter, people say screened instead of the word transparent. I'm using transparent because screened could mean several things. Transparent means that it cannot be detected by any bulk observable. So why is this claim completely trivial? It's trivial because by definition, if a line operator L is my line operator, if it's charged under one-form symmetry, then there is a phase that you can detect by wrapping it with a one-form symmetry charge. And this phase is some root of unity in the invertible case. I'm talking about just ordinary abelian one-form symmetry. So since you can detect a phase by wrapping the line defect with a one-form symmetry charge, by definition, it's not transparent. So this is a completely trivial statement. Are there any questions about it? So what this equation means is that there is some way to measure in the bulk the presence of this impurity, because you can construct this non-local observable. This is drawn in 2+1 dimensions, where the line operator and the one-form symmetry charge are both codimension 2. So you can construct some weird non-local observable that would detect the presence of the impurity. A less trivial statement is that if the one-form symmetry surfaces can be cut open, sometimes people say that this means that they're endable, then you can make a much more impressive inference, which is that the line defect cannot flow to a topological line. Previously, you could say that this equation does not constrain the infrared limit completely. It forbids a transparent line, but it still allows a topological line in the infrared, a topological impurity. So there could still be no displacement operator. But the claim is that if the one-form symmetry charge can be cut open, then the displacement operator literally cannot be 0. So this is much more strong. It forbids L from flowing to a topological line, and it forces L to have non-zero response to moving the impurity around. So in this case, most likely it ends up being a conformal line operator, non-trivial conformal line operator. Okay, how does the proof go? The proof is just evident from the picture, because if L was topological, moving it one way, you would pick up a phase, and moving it another way, you would not pick up a phase. So you would reach a contradiction if you assume that the displacement operator vanishes. So this allows us to conclude that defects that are charged under endable one-form symmetry must have a non-zero displacement operator. And this implies a conformal defect at long distances. So if you have a system with one-form symmetry, like some CFT with one-form symmetry, you can constrain the infrared limit of some line of some impurities. And this is especially interesting in gauge theories, where Wilson lines carry one-form symmetry charges, or 't Hooft lines carry magnetic one-form symmetry charges, and so on. Actually, since I will be discussing applications for magnets today, I will not be using this theorem. Okay. Now I'll explain the next thing, which is actually very useful in magnets. It's another theorem about the infrared limit of defects, which turns out to be very useful in magnets. So for this, we'll have to understand the implications of zero-form symmetry, how zero-form symmetry acts on line defects, which, as you know, is a more interesting subject because the interplay of zero-form symmetry with line defects is interesting and rich. So you have to think about two separate cases. Both of these cases will be important today. So the first case is when the line explicitly breaks the symmetry. So the theory on the line, think about this example before. You write some kind of coupling of the line operator to the bulk, and you can also add quantum mechanical degrees of freedom on the impurity. And so one case is that those interactions just completely break the symmetry G, or break G to a subgroup. Okay? So in this case, the symmetry G is broken by the line operator. What are the consequences of that? Oh, I'm assuming that it's not broken in the bulk, of course. I'm assuming that it's broken only by the line operator. So we can consider the following configuration to understand the consequences of an explicitly broken symmetry. We take the line operator, make a circle out of it, and wrap it with a zero-form surface, like this. So if the line operator breaks the symmetry G explicitly, we expect non-zero one-point functions for operators charged under G. This is like in one of the previous slides where we had one-point functions. So if the symmetry is broken explicitly, we expect one-point functions. But now we see that given this construction, the one-point function will have to jump because local operators, when they cross a zero-form symmetry surface, their expectation value changes according to the action of the zero-form symmetry. So we see that the VEV would jump across the zero-form symmetry surface. This shows that if we fuse the line operator with the zero-form symmetry surface, we must obtain a new line defect where the vacuum expectation values of various operators are transformed. Because we see that the presence of the surface changes VEVs, the fusion must create a new line operator. So you can think about this construction as creating an effective new line operator. For continuous symmetries G, this leads to a very nice implication. So we can think about continuous transformations G as being infinitesimal. And hence the fusion can be implemented by integrating a local operator on the defect. And you must obtain some new defect with transformed vacuum expectation values. So therefore, this leads to protected operators on the defect, which are called sometimes the tilt operators. I think that this name tilt was invented by Marco Maineri, if I'm not mistaken. But they appear in condensed matter under different names too. So if in general the symmetry G is broken to a subgroup H, then these parameters are living in the coset G mod H. So we see that an explicitly broken symmetry by a line defect leads to protected operators that live in the coset. And this follows from the fusion of the continuous zero-form surfaces with the line operator. Are there any questions about the existence of these protected operators?
When you say explicitly broken, you mean explicitly broken on the line to a subgroup H?
Yes, explicitly broken by the theory on the line or its interactions with the bulk, or both, but not by the bulk theory, which is assumed to have a G symmetry. So for instance, the bulk theory could be a Heisenberg magnet, but the coupling here could only pick out like one of the spins, and you would destroy SO3 symmetry in this way. Okay. Are there any questions about the existence of these protected operators? Usually when a symmetry is broken explicitly in quantum field theory, we don't use it, it's useless. But when it's broken just by a defect, we see that it leads to interesting protected local operators. And they're important because they describe the fusion of the zero form surface with the line defect. Okay. A much more abstract situation is when the symmetry is preserved by the line and by the couplings to the bulk, because then the fusion is trivial. Why is the fusion trivial? Because there are no order parameters that will have one-point functions if the symmetry is preserved. So the fusion doesn't actually change any local operator expectation values or any green functions, and therefore the fusion is trivial. So you might think that, okay, if the symmetry is preserved, then there is nothing to say. But maybe you already anticipated that's not the case. So from the operator product expansion of bulk operators in terms of defect operators, it is very clear that defect operators are in linear representations of the symmetry G, which is also true for bulk operators. So we see the defect operators are in linear representations of the symmetry G, or the impurity operators. And the same is true for bulk operators. But what about defect changing operators? It's very difficult to prove that defect changing operators are in G representations, and that's actually not true. If you have a local operator that changes one defect to another defect, it may not be in a linear representation of G. So those could transform in projective representations of G. For instance, if you have a magnet with SO3 symmetry, defect changing operators could be in a projective representation of SO3. And this leads to interesting constraints on our G flows that we will explore today. So what does it mean for our G flow? Actually, if the defect changing operators are in projective representations of G, this leads to a rigorous conclusion about the infrared. So if the lines flow to a transparent trivial line that are not stacked with 0+1 dimensional TQFT, then the defect changing operators cannot be in projective representations. So therefore, just knowing the defect changing operators are in projective representations rules out a scenario in which the line is completely screened and completely trivial with no 0+1 dimensional TQFT. Or in other words, if you want to be a little bit loose, you could say that this situation where there are projective representations among defect changing operators leads to the conclusion that some line operators cannot be completely trivial. They cannot flow to the unit operator. You either have to flow to a topological line, or you have to have some 0+1 dimensional TQFT, or something else. It might be a conformal defect or various such things. But you can rule out the scenario where some line operators are just completely trivial, just from this fact that defect changing operators are in projective representations. Are there any questions about this theorem? Okay. So this constraint is weaker than one-form symmetry, because using one-form symmetry, we concluded that the displacement has to be non-trivial. Here, we cannot conclude that the displacement has to be trivial. It has to be non-trivial, I meant. It could be that the displacement operator is trivial, but we still have to have some degrees of freedom remaining at the infrared. They could be decoupled from the bulk. It could be just a stacked TQFT, yet there should be some degrees of freedom left at long distances. So you'll see that this has some implications. Okay, so now the final constraint that does not concern with specific examples, just a general constraint. A very canonical observable that you very well know from the study of topological defects is the expectation value of the circle. The expectation value of the circle for topological defects is called the quantum dimension. It's independent of the size of the circle. For defects which are conformal or that there is an RG flow, for defects where there is a non-trivial RG flow and they are non-conformal, the expectation value of the circle has a dependence on the radius, and we call it the defect entropy. So you take the expectation value of the circle, you apply this differential operator where R is the radius of the circle, and you get something that we call the defect entropy. You need to apply this particular differential operator to cancel some scheme dependence, which is a lattice regularization if you want artifact. So there is so you can think about the expectation value of the circle as a function of the radius, which is tracking the RG flow. So when the radius is very large, it's like the infrared limit. And when the radius is very small, it's like the ultraviolet limit of the impurity. So there is an interesting scheme-independent observable, which is called log G, or the defect entropy. Of course, it's difficult to measure it. Now, in topological filter, the quantum dimension is known to be bigger than 1. So log of G has to be positive. But you will see today that for conformal defects, it is very possible that log G is negative, but unitarity requires G to be positive. So log G could be arbitrarily negative, but still G has to be positive. So the logarithm is well-defined. Okay, so this is an interesting observable, which is called the defect entropy, and it generalizes the notion of quantum dimension to the world of non-conformal defects. Why am I introducing this quantity? It's because it's possible to prove this very nice inequality. As you increase the radius, the defect entropy must decrease. And that means that the quantum dimension at short distances must be bigger than the quantum dimension at long distances. And this is a completely non-perturbative constraint on impurities. And now, using the previous claims, we can convert these things into actual inequalities about RG flows, and they will have implications for magnets, both of them. So first, we can say that if we have a defect where the defect changing operators are in projective representations, then we already said that the flow cannot end with a unit operator. You have to have some stacked TQFT. That leads to an inequality connecting the UV quantum dimension and the dimension of the Hilbert space of this 0+1 dimensional TQFT. This inequality must be obeyed for any conformal defect, for any defect which ends up with a trivial line operator stacked with a 0+1 dimensional TQFT. A particular case is when the TQFT is trivial, then you get this inequality. So the logic is that you assume that such an RG flow exists, then it has to obey this inequality. And of course, the way it's actually used is that we will assume that it's true and then reach a contradiction. So that is how constraints are placed on RG flows. Are there any questions about this or the preceding discussion? Okay, now I'm going to go through two examples, which are defects in magnets, and I'll show you how both of these have applications. And they settle some problems in condensed matter. So first of all, I'm going to describe a line defect that is called the pinning field. I'm going to explain now what it is. So we take the Wilson-Fisher fixed point with ON symmetry. You can ignore this. I'm mostly interested in 2+1 dimensions. So D is equal to 3. So there is a question of what happens when you put an external magnetic field, but instead of putting it throughout the magnet, you put it at one lattice site. So the red blob from before doesn't actually have to represent the new degrees of freedom that couple to the other lattice sites. It could also represent turning on some external field at one lattice point or a few lattice points. It doesn't matter. So there is a question of what happens to magnets when you do that. This is represented by this line defect. So you essentially add the first component of the ON vector field, which is the ON Wilson-Fisher vector, at one point in space, at x equals to 0, say. So this is localized at x equals to 0. So this particular line defect breaks the ON symmetry explicitly to ON minus 1, since we have chosen a direction for the magnetic field. So this will be in one of the situations we discussed before. Another thing is that this is a relevant perturbation. So by the G theorem that we discussed before, G has to be smaller than 1, because G in the ultraviolet is 1. And this means immediately that the external magnetic field cannot flow to a trivial line operator. So this line defect cannot end up being screened or transparent. So this is, if it were, then this would have to be true. But since G of V is 1, this cannot be true, and you've reached a contradiction. And that means that this external magnetic field cannot be screened, and it has to furnish a conformal impurity at long distances. And it's a very interesting conformal impurity, which is very easy to measure, because it comes from, you tune to the Curie temperature, and if there is some remaining magnetic field in some part of the sample, it will flow to this defect. And you see that we can use this G theorem to claim that it cannot be screened at long distances. So there are many simulations and experiments concerning this situation. So these are some recent references. So what can you do as far as a theory goes? You can do, of course, epsilon expansion. You can do some sort of consistent Schwinger-Dyson analysis. I'll quote some results from these two. Maybe you can do expansion around 2 dimensions, and this is much more difficult. But I'll just quote some results emphasizing the points that are relevant to what we discussed before. First of all, the G function, the quantum dimension of this defect, is negative. The log of G is negative. So that's an example of what I said before, that there is that it doesn't, unlike topological lines, it doesn't have, the quantum dimension does not have to be bigger than 1. You can also compute anomalous dimensions of the magnetic field. You can also, I'm not going to go through that because it's impossible to explain in 5 minutes, but there is an exact large N solution of this defect that we found a year ago. And it can be used to make many predictions. And there is a lot of work on this subject from recently. But this is like some examples that at large N, you see that indeed log G is exponentially small. And this is the defect dimension of some leading magnetic field perturbation. It's a stable infrared fixed point. And it's completely consistent with the G theorem, because we found that it's a conformal defect, it's not screened. Finally, I gave you a proof before that if a continuous symmetry is explicitly broken, there must be protected operators. And you can find both in large N and in the epsilon expansion that this is indeed the case. We have these tilt operators that parameterize the coset ON divided by ON minus 1, which is a sphere. So everything is consistent. It's an interesting defect that obeys the G theorem, and all is good. I just wanted to finally mention that these large N predictions seem to be more or less in line with simulations and Monte Carlo simulations and experiments, but the precision is not very high yet. Okay, so if there are no questions about it, I'll go to the next example where the symmetry G is not explicitly broken, and we can use the other theorem about the 0+1 dimensional TQFT that has to survive at long distances. Are there any questions about the pinning field defect? Good. So this is so here this defect does not correspond to turning on a magnetic field, because that breaks a symmetry explicitly. Instead, we do the following interesting thing, which fractionalizes the symmetry. It leads to projective representations. So let's consider the ordinary magnet, O3 Wilson-Fisher model. What we do is that we take one latticite and put a spin S representation of SU2. So we couple a Hilbert space of dimension 2s+1 to the bulk. And the coupling is through this term. So SA are the operators that act on this internal spin in the representation of spin S. And they couple to the order parameter of the Wilson-Fisher model. And you sum over A. to preserve O3 invariance. Gamma is the strength of the coupling. So you can think about this interesting line operator as a close cousin of the Wilson line, even though this is not a gauge theory, it's just the Wilson-Fisher model. It has line operators that very much remind us of Wilson lines. So we simply trace the order parameter dotted with the spin operator in the representation S. So the question, it's been an interesting question, condensed matter, of what is the infrared limit of this system. So you just replace one of the atoms by a spin S atom. Okay. I should say that sometimes this model is called the Kondo boson model because it's a very close cousin of the Kondo problem in 1+1 dimensions. You can think about it as a Kondo problem in 2+1 dimensions. Okay. So I already said that you can realize it easily. And now let's talk about the topology of this situation. So we have a Hilbert space in a spin S representation of SU2, coupling to the bulk. But clearly, defect changing operators that take a Kondo spin S to a Kondo spin S prime would have to be in projective representations of SO3 if S minus S prime is a half integer. Is that clear? Or should I explain it again? Or explain it in a different way? Well, one way to understand it intuitively is that in the O3 Wilson-Fisher model, all the operators are in linear representations of SO3. But now we couple some spin S representations via the adjoint. So if you want to, let's think about endpoint operators that take the trivial line to a line of spin little s. So there is no natural endpoint from the bulk because you have to make the spin jump by a half integer. So from what we said before, we learned that the infrared cannot be trivial. So it cannot be literally the unit operator for lines with half integer spin. And this is, of course, very intuitive physically, because once you put an atom like this in an antiferromagnet, you can dress it up with bulk excitations, but you can never change the spin by a half integer. You can only change the spin by half integer. So no matter how the response of the magnet goes, it cannot completely screen a spin which is a half integer. So technically what it means is that the infrared cannot be a trivial line with no degrees of freedom. So let's consider the S equals a half case, which is the most easy to access experimentally and in simulations. So from the previous theorem, from this inequality that I quoted here, we can learn something immediate. Because the ultraviolet G function is 2, this is the dimension of the Hilbert space that we couple to the O3 model. And if it was completely screened, also the infrared G function would be 2, and this violates the inequality. So we reach the contradiction. So this actually solves a pretty canonical problem in 2+1 dimensions, which is the Kondo problem in 2+1. It shows pretty rigorously that the S equals a half spin cannot be screened. It has to flow to a conformal defect. And some things can be understood about this conformal defect. So theoretically, you can do an expansion in 1/s. You can do an expansion around 4 dimensions. So we don't have access to computing observables exactly for S equals a half. This line operator is pretty complicated, but you can get good approximations. People invented an expansion in 1/the spin. That's what we did in one of our papers. Also, people did before some epsilon expansions. And indeed, the combination of the two methods suggests that the S equals half is not screened, and it's a conformal defect with some properties that we can estimate. So this is just references to some additional work on the subject from recently, both from the condensed matter and the high energy group. Some of these papers, I should say, do not address this problem directly, they look at the multi-critical Wilson-Fisher model, namely just the mean field theory, which is a simpler problem, but still hard to solve analytically. For the interacting case, there is not much data, but this theorem proves that it cannot be screened. Okay, let me just summarize what I've shown. I've shown that arguments from symmetries and topology, combined with rigorous constraints on RG flows, lead to interesting conclusions about infrared limits of defects, even in very simple theories like magnets, Landau-Ginzburg models. Of course, you can also play with games with gauge theories and so on and so forth, but I don't have time to go through that. So I just wanted to show you some applications of topology for defects in magnets. These predictions are testable. People have started testing them. Some tests existed before, and they pretty much seem to be consistent with what theory predicts. So that's more or less what I wanted to say. So thank you so much. Okay.
Are there any questions?
So much. Yeah. There are any questions? I can try to answer them. I don't see any questions in the. I don't see any questions. So
If you mentioned at the end, the experiments seem consistent. If there were a discrepancy, what would you say? That the symmetry is just somehow not there?
if there were discrepancies.
Just hypothetical experimental discrepancy.
Well, what the like for instance in the last case that I mentioned, which is the Kondo spin in the Kondo spin in 2+1 dimensions. Yes, the theorem predicts that it cannot be screened. That's what's seen experimentally, but that means that it flows to some conformal defect. It means that this line operator is a conformal line operator in the O3 model. It's an interesting conformal line operator, but if you want to get predictions for, not just that it's not screened, but actual predictions for the scaling exponents and the bulk response, I don't know, the various concrete predictions or these 1-point functions that people sometimes measure. They measure these 1-point functions that I mentioned. That is much more difficult. The general theorems only predict that it's a conformal line operator, but if you want to get actual numerical predictions, you have to resort to some approximate techniques. We cannot solve it directly. So we did a lot of work a year ago about developing an expansion 1 over the spin. There is some very technical work on the epsilon expansion with some scaling limits. They seem to converge on an answer that's roughly in agreement, but of course these are just extrapolations from theoretically controlled expansions. So I'm just saying that roughly there is an agreement, but I don't know how precise this agreement can be made. Ultimately, it has to be settled by numerics or experiments or bootstrap.
Thanks. Are there any other questions? Yeah. Okay, let's thank Zohar again.
Thank you so much. Thank you. Enjoy the conference.
Thank you, Zohar.
Thank you.